Okay, so I'm back, and we just got finished talking about the tides and how the gravity of the moon pulling on the water of the earth can cause the tides. But remember that the gravity of the moon is also pulling on the earth itself. And so if you look at the crust of the earth, you'll notice that the crust actually rises to meet the moon every time that it goes over your head, and it rises about 1 centimeter. And it's not just the gravity of the moon, it's also the gravity of the sun. So the sun pulls on the earth and raises it by about a half a centimeter. And you can also see from that chart that the gravity of the moon pulls on the water and causes it to rise by about 25 centimeters. So the moon causes the oceans to rise by about 54 centimeters. Then you add into that the effect of the sun. So, for example, let's pretend here's the earth, here's the moon, and then let's put the sun over here. So the sun would also be pulling on the water, and the moon would be pulling on the water. So you would add them together, and that's going to be called a spring tide when they both combine to give you an extra tall tide. On the other hand, let's put the moon here so that the moon is pulling the water this way, but the sun's pulling the water that way. And then what happens is you subtract those two numbers, 54 and 24, subtract them, and then that's an extra low tide. So that's going to be a neap tide. Okay, then the moon is pulling on the continents as well. So it's pulling on the crust, and so it pulls up the crust by about 1 centimeter. The sun does the same thing, so the sun pulling on the Earth's crust is going to pull it up by about 0.5 centimeters. And the atmosphere. So the atmosphere of the Earth is pulled by the gravity of the sun and the gravity of the moon. Well, there's one more thing that's going to happen, and that is, according to Newton's third law of motion, for every action there's an equal and opposite reaction. So that means that if the moon is pulling on the earth, then the earth must be pulling on the moon. So that the crust of the moon is also going to be pulled by the gravity of the earth, and it rises by 0.25 centimeters. Not very much, because of course the crust of the moon is very rigid and it doesn't like to be bent that much. And then the sun also pulls on the crust of the moon. Okay, so we now know that the closer that an object gets to a moon gets to the planet, the stronger that gravity gets. So the stronger this tidal force is going to be. So they've even worked out the formula for it. So if you look at that formula, there's the force of the tide, and you notice it's got the big G in there because the force of gravity had the big G. It's got the mass of the planet, and it's got the mass of the moon, just like this. But it also has the radius of the planet, and it also depends on the distance between the two objects. So notice as the r gets small, so as this thing is being, if you take your moon and move it towards the planet, the r is getting small, so the tidal forces would get stronger. So that would mean that instead of the water bulging like this, if we move the moon closer, now the tidal bulge might be like this. Okay, so you see that the closer that the moon gets to the earth, the stronger the tides would get. And according to Newton's third law, the stronger the tides would be on the moon caused by the earth, so that the moon would begin to stretch. Well, in our next segment, we're going to talk about that those forces could get so big it could rip a moon apart. So stay tuned for the next segment.